Welcome to part 3 of video series on relational databases, giving you informal introduction. In this part, we will concentrate on very important design guidance for relational databases, and this is about storing one entity in one table, or it could be one table allocated to one entity. And now about another problem, which is also pretty common, which is also something you will see very often in real databases. And this problem is known as mixing different entities in one table. What is entity in databases? Entity is actually object type. So it's actually some object you want to store in your database, and this object has some properties. For example, for a customer, you may want to store his name, first name, last name, his address, phone number, email. So in this case, customer is considered to be your entity. This is one single object you want to store information about. And the general rule of good design is one table, one entity, or it could be read vice versa. One entity goes to one table. So rule is you should not mix different entities in one single table. Let's see how it may happen. This table is some kind of table for, let's say, some kind of financial agency which is renting mortgages for their customers. And in these tables, as you can see, they store name and address of the customer, their phone numbers. They also store information about mortgage type, which was allocated to them, mortgage rate, is it what kind of down payment was made, and about the property which this mortgage was covering, square footage, bedrooms, bathrooms, all information about property. So what is wrong with this design? And it's actually a possible design. It's possible to store it this way, but it's very inconvenient, and it will actually cause many troubles in future if you really store it this way. The problem with this, we are trying to mix different entities in one table. As you see, this group of fields actually describing customer. So name, address, and phone is about customer. Now, the next group of fields is describing mortgage. So it's not describing customer. So mortgage type, mortgage rate has nothing to do with customer, with who this customer is, what is his name, and where he lives. And the last group of fields is describing property, which is covered by this mortgage. It's yet another entity. So we have three separate entities: customer, mortgage, property. They're all mixed together in this table. What kind of problem we will face with this? First of all, we already know from previous explanations that we should not actually mix objects of different cardinality in the same table. And this is actually something what happens here, even though it may be not immediately obvious. Because number of records for each entity could be different. For example, the obviously possible case that the same customer has more than one mortgage. In this case, there will be one customer, but more than one mortgage. And it could be other way around as well. There could be one mortgage and more than one customer. For example, if married couple, husband and wife, if they're paying for mortgage together, in this case, it's one mortgage, but two persons. And the same goes about to property. Property is even more separate entities than to previous one, because a property description doesn't change. However, mortgage can change very often. So some properties could be remortgaged. So you can close one mortgage, open another mortgage on this mortgage. Term could be changed all the time, where square footage of the property and bedrooms and bathrooms is the same. And it's the same situation with cardinality. We have more than one mortgage for the same property. We'll have more than one property for the same mortgage. For example, it's all possible combinations. So this type of design is highly discouraged, and it's much better to avoid it. When I said previously that repeated groups could be allowed in some cases, and those cases, if you remember, were cases where we do not care about this information, where we only store it for some kind of archiving purposes. Now, this design, when we mixing entities in the same table, it's almost never good. So almost never it would be good because we always care about this property. So we cannot say that we don't care how we store this information. We just store it for future because we simply wouldn't be able to store it properly. And another thing to mention, just the consequence of bad design, what could happen, for example, in this case. Let's say that I added another column to this table, which is called last update. This is a very common type of column. Very often we need to know when we last updated our information, so how fresh our information is. So it obviously refers to the time when this entire record was updated. But now there is a very interesting question, what exactly was updated? Did we update information about customer? For example, did he change his address? Did he update information about mortgage? For example, we now giving him different rate. Or did we update information about property? For example, we found some mistake in the property description and decided to update. Now, this last update is pretty vague. We don't really know what was updated. However, if information was stored properly, and properly means that separate table was allocated for customer, another table for mortgage, and another table for property, they all will have this column last update, and in this case, this column will not be ambiguous because it will be pretty clear what this last update refers to. We already reviewed so many cases of design mistakes or bad designs. So now you probably have very natural question, what is actually good design? So how to solve all these problems which we just identified. So if these are cases which are not recommended or discouraged, then what are actually correct approaches? And correct approach almost in all cases is to split information between tables. So in other words, you need to create more than one table and you need to establish some kind of relationship between these tables. Let's have a look once again at our table, which we already seen many times. What we can see here is actually that some information is still duplicated here. We already eliminated duplicated rows in table, but if we, for example, look at branch column, we can see that some values appear more than once. So, for example, Milford is used more than once. What would be actually correct way of implementing this table? We need to apply so-called normalization to this table, actually to this particular column. And the way to do it is to introduce tables instead of one. One will be still table employee, our original table, and another table is branch table. Branch table will only hold information about branches. So it will have nothing to do with employees. As you can now see, we gathered all branches together and we assigned ID to them. So we have created a primary key to this table, so we can now use this branch ID in our primary table. And if you now look at employee table, instead of mentioning branch name, it now has branch ID. So these two tables carry essentially the same information as previous table, but in very different form. Now this, at least this information branch is normalized. And now after we split this information about branch and put it into different table, what benefits of this we actually now experiencing? What are benefits of this change? Well, the first and most noticeable benefit that you can now change data independently. So let's say you need to change something about your branch. Probably you need to change name of this branch. Right now, you can go ahead and change it in this name in branch table, and you don't need to do anything else. Your employee table doesn't require any change because it doesn't store this name anymore. It will simply refer to a new name automatically. Now, in previous design, if you needed to change branch name, you will need to go ahead and change it in all records in your table. And the biggest problem of this is not this job itself that you need to change it. The biggest problem in this, and this is coming from real experience with databases, the problem that you will almost always forget to do this. It's quite possible that your branches are used in many tables, and if you rename branch in one table, you will probably forget to rename it in different table. Especially it will be true if you have many hundreds of tables. And after that, your tables will become not synchronized with each other. One table will still show old branch name, and another table will show new branch name, so you will have some mess within your data. Now, if you store information only in one place, and relational database structure actually encourages you to do this, as you probably already understand, relational database very much dislike duplication of data. And the biggest reason of this is that if you have only one copy of data, if you need to change it, then in this case, it's always safe. You do this change, and this change is reflected elsewhere, not only in one place, but an entire database now is picking up this change. Another very big benefit that you can add more columns later to this branch table. Let's say that you wanted to store more than name of this branch. You also want to store address, fax, and you also needed to store some logical flag open on Sunday, which is either true or false. So some branches could be open on Sunday and some branches are not. You can very easily add it to this, and now all your records in employee table automatically picking up this information because these two tables are linked together by this branch ID. So now you can easily see whether a certain employee is supposed to be working on Sunday or not. Previously, you will have, if you wanted to do this information, you will have to store all this information within employee table and just think what kind of mess it would be if you store branch address, fax numbers, just together with employee information. And obviously, it will be duplicated many times. And another very big benefit, I already slightly mentioned it, that you can reuse this branch table elsewhere. So apparently, it's not only employee who is associated with branch. Apparently, you also have orders, you have customers who also could be assigned to certain branch. So you have one single branch table which serves not only your employees but your order table as well. Now they all can be pointing to this branch table and they will all benefit from just single point of change if you need to change anything. For example, if branch was open on Sunday but not anymore, you simply update one record and your employees now not working on Sunday, your orders which are assigned to this branch are now not handled on Sunday. So you actually reflected this change everywhere. So as we now see, we actually established some kind of relationship between employee table and branch table. And the relationship is there is a branch ID column within employee table which points to ID column in branch table. This kind of relationship is commonly known as foreign key relationship. Where this name is coming from. Your ID column is primary key in branch table. But in employee table, it's called the column branch ID, which correspond to this is called foreign key. And foreign key comes from the fact that it was borrowed from another table. So it was natural key or primary key for first table, but it is foreign key in another table because this another table, in our example, employee table, is using some kind of key from which came from another table. So this is called foreign key relationship. Most relational database products will allow you to do something which is called enforcing foreign key relationship. It means that you can somehow set up in your product that you can explain to your product that this is foreign key, not just some random column. And in this case, your product will track that data in both tables are consistent. It means that it will not allow you to use branch ID in employee table if there is no such ID in branch table. And vice versa, it will not allow you to delete record from branch table if there is some kind of reference in employee table or in any other table. Whether to enforce this foreign key relationship or not, it's up to you. It depends on how important it is for you. Sometimes you want to enforce it if it is critical for your business that you do not have so-called hanging references, that you do not refer to the record which doesn't exist. But sometimes it's a little bit difficult because it restrains you when you're doing some maintenance, when you need to move records around from one table to another. Sometimes it will be difficult if they're closely tied to each other. Another important term which we need to learn is that this kind of relationship, this kind of which we currently see on the screen between employee and branch, is also called one-to-many relationship. And this is because you will have one record in branch table and many record in employee table which correspond to this record. So this kind of relationship explain this problem from the point of view of cardinality. We already heard this term cardinality in previous slides. So you have different number of records. So your cardinality of employee table is higher than cardinality of branch table. And this kind of relationship from the point of view of cardinality is known as one-to-many relationship. So let's now see how all this works in practice. I just dropped our previous employee table and created two new tables, one called employee and another called branch, and these are just tables we were talking about before. And actually it was too easy for me. I could just drop table and create another one, but in real life you would not have such benefit. In real life you cannot simply drop table and create another one because your table will have some data, probably data about your customers or which belongs to your customers. So normally you will need to run what we already talked about before, and which is called conversion process. So you will need to run some SQL script to develop some application which will be converting your data. However, when creating education material, I can do it just easier. I can simply delete and recreate it. So I already deleted tables and I already recreate them by running this script which I'm currently showing to you. You already know create table statement. You already understand how it works. There are two new components in this. First of all, you can look at this new data type called bit, and this is actually SQL Server data type for logical fields, which is a 0 or 1 as a false or true. And another important thing to notice, you can have a look actually how I approached creation or design of ID in both tables. In employee table, our ID is declared with identity flag, which means that it will be auto-incremental field. It means that SQL Server will assign these values itself. Now, if you look at our branch table, there is no identity here. It's just simply regular field. So SQL Server will not create any values for this, and this is done on purpose. This is because branch table is a little bit different in terms of business use from employee table. Branch table is so-called reference table, or another term you can come up with is dictionary table. So these kind of tables, they store somewhat static information. Static means it's almost never changing. So our description of our branch is very stable. So sometimes it may change, we can open another branch, but normally, under normal circumstances, it's not changing. And this is why it's very important for us to maintain this ID on our own. We don't want that SQL Server assign this ID. We want to know which ID we assign it to each branch, because we may have some code, we may have some software which would be aware of this ID. So this is why first table has it as identity and the second has it just as a regular column. And another thing I wanted you to pay attention to, you can actually look what data type I selected for branch ID, and obviously as a result of branch ID in employee table. As you see, it's tiny integer. We already talked about this point before, that sometimes some developers will allocate to big data types, and it's pretty common to declare this kind of fields just integer. But integer is 4 bytes, and 4 bytes is capable of storing a value of 2 billion plus. Obviously, we don't have that many branches. Tiny integer, which allows us to store values up to 255, in most cases will be appropriate, because most companies will not have that many branches, or just in case it's very really big corporation with more branches, we can define it as small integer, but never as an integer, because for this kind of information we need that big field. Now this is how our new insert statement looks like, or to be more precise, two insert statements, because we now have two tables. You already know how insert statement works. The only thing to notice is once again that I'm inserting ID for the second table, for the branch table, and not inserting ID for employee table, because this is where it will be assigned automatically. And now for the most interesting part, how would we now query these new tables? So let's first have a look at these tables themselves, what data they have. If I want to execute only some statements which are shown in this window, I can always highlight them and click on Execute button. In this case, only this select from branch statement will execute. You can also use this technique if you are following these examples. If you do not highlight, then it will execute all statements in the window. And right now I wanted only the first one. So you can now see how our new branch table looks like. Let's check our employee table. It's almost the same as it was before, except that branch name is now represented. It's now replaced with branch ID. And the most interesting statement is the third one. This statement is going to look at these two tables together. And as you can see, we're now looking at different form of select statement. Previously, it was select from some table. Now it's select from first table, which is employer. Then we have second table, which is branch, and we join them. You see, there is actually join clause here. So our employee table join to branch table, and we also specify how do we join it, on which columns we join it. So we say that within employee table, we take branch ID column, and within branch table, we take ID column, and these columns should be equal. So this is how our join will work. And the rest is something you already know. This is where clause, and within where clause, I want only those employees who are possibly will be working on Sunday. So I only wanted employees who work for branches which could be open on Sunday. So this is actually our statement. Let's highlight it and let's go ahead and run it. And we can now see a table which was returned by this statement. It did find that only 2 employees actually matching this restrictions that they will be possibly open on Sunday. And at the same time, it's actually a good example which is showing the efficiency of using this star within select statement. First of all, you can see that too many columns were returned. And if you use star within statement which joins table, in this case, it will return all columns from all tables. In our case, it's not yet that bad, but imagine that you can join 10 tables, and this is not uncommon. You will very often have select statement which is joining 10 or even more tables, and imagine how many columns could be returned in that case. But just the number of columns is not the biggest problem here. One problem could be actually seen if you look at this bottom portion of the screen. You see that ID column is now we have 2 copies of ID columns. There is one ID column which is coming from employee table, and there is another ID column which is coming from branch table. So you now have duplicated names, and this is obviously very confusing. And another thing which is not bad, that you really return columns which you are not supposed to do. For example, why would you return this open on Sunday? Your query is only looking for records which have open on Sunday 1. So returning this column is redundant. So the better way of doing this, I will just type in first name. I use IntelliSense and SQL Server. It actually prompts me with possible column names from here. First name, last name, and probably I want to know position, who these people are. So that would look back. And also, normally I will have order by clause as well, because normally I want them to be presented in certain order. So I will order by last name first. And then if they happen to have the same last names, then let's put first name as well. So that statement looks better. Let's execute this. And now you see actually that we have our results in way more convenient form. So finally we wrote nice SQL statement and have nice results. So we just introduced you to query with joins, and from now on you can expect that most of your queries will have some kind of joins. This is because joins are almost everywhere in relational databases. They are used very often. Now, there is actually a very interesting question, is it good or bad? And actually it's both. Because joins is one of the strongest features of relational databases. At the same time, it's one of the reasons of the main weakness as well. So you see, the same thing could be strong and weak at the same time. It's a little bit tricky, but it very much depends from which point of view you are looking at this issue. Uh, from one side, join allows you to keep only one copy of data and use it everywhere. This was just illustrated in our example with branch table. We have only one copy of information about each branch, and we can use it everywhere, not only employee table, but other table can refer to it. So many table can take advantage of referring to this single copy of information. Another important point to mention that most database products, I mean relational databases, of course, will apply some optimization to joins. And this is because your product is aware that you will be using joins all the time. So your product knows that you need use it intensively, and it will try to do its best to do the join effectively. For example, in SQL Server, there are many types of joins, there are different strategies. We will not be covering them at this time, but just to make a note, the SQL Server will try to apply some best technique available when it's making join. So you can expect that joins are performed more or less effectively. Now, one of the biggest problems with joins is that the ubiquitous joins are obstacles for making multiple server systems. There is a common tendency now in database world, because it's very much now oriented to handle very big amount of data. There is a common tendency to build database which are split between different servers. If you are doing very often joins, obviously you're facing problem. How will you join your records between servers? So making cross servers joins when one table is on one server, another table on different server, and they need to join together. It's not going to be performance effective. It would be overstatement to say that it's not possible to build multiple server systems at all on relational database model. There are some projects which are trying to do this, but it's definitely an obstacle. And I think it would be fair to say that relational model doesn't feel comfortable within multiple server world. And another problem, if you have many tables in query and you join them, sometimes it's difficult to work out the best way how to perform this query. So sometimes it's difficult to read this query, and it is sometimes certain complication for your product to understand how to execute this query in the best way. Although your product will try to do the best to do it better. So previously we looked at the case where we have multiple levels of information. We have customers, and each customer has one or more order, and each order has one or more items. And I promised that we will fit this schema perfectly into table. Actually, it fits really very easily into tables, and this is one of most classic examples. These customers, orders, and order items, I think you will see them everywhere in articles, in some education materials. So this is actually a pretty classic example and still pretty practical. Obviously, we cannot fit all this information into one table, but the solution here is to use three tables. So there will be a table for customers, which store all information about customer and only about customer. It doesn't store anything about orders or order items. And there is another table called order, which only stores information about orders and nothing else. And there is a third table called item, which only stores information about order items. And obviously, there is a relationship between these three tables. Order table relates to customer table by foreign key relationship. It has customer ID, which is equal to ID in customer table. And as you can guess, item table has the same relationship with order table. It's also foreign key relationship. It has order ID, which points to order. So what is very important about this data schema? It's actually showing you concept of separation of concerns, because each table is only corresponding to certain entity. You know, we have rule one entity, one table. And each table is only concerned with information it stores. I would say it only cares about this information. For example, customer table has things like name, address, customer type, maybe some rewards this customer have, and knows absolutely nothing about orders and items. This is not concern of this table. Order table has everything about order. It knows nothing about item, and it has some very, very limited, I would say, tiny knowledge about customer table, and this knowledge is just the fact that it stores customer ID. So it has some relationship to this table, but this is everything it has. Other than storing customer ID, it knows nothing about customers. And subsequently, item table knows nothing about order except of having order ID, and it concentrates on item. It's very interesting to note that item table actually also knows nothing about customer table, even though obviously they are logically related. But item table is related to customer table only indirectly, only via order table. There is no direct relationship here. So this schema can perfectly handle actually everything we need, and actually you see that within item table we have columns like price and quantity, which allow us to calculate total for this order. Now, it's very interesting to note that people who are actually strict with database schemas with normalization will probably point it out that this schema is also not perfect, and this is because it stores product information within item table. Normally, you will have actually the same product sold for many customers. So normally you will have another table called product, and your item table will probably have product ID, so it will be referring to this table. So this would be right way to do this schema. However, we simply cannot do everything at once. So at this point, let's just concentrate on these three tables. There is one more important thing to note, and this is about possible inclusion of amount column into order table. Each order has amount. It's total for this order. It's how much customer should pay. Now, there is a very interesting question. It's actually a very difficult question. It's not even easy to give direct yes or no answer to this question. Should we really have this column? And why we are concerned with this column? Because this is actually example of denormalization. We already noted this term denormalization before, and this is a perfect example of what denormalization may look like. And why it is denormalization? Because this amount is also known from item table. So if you multiply price to quantity, you will have actually total for this line of items. And if you summarize all items for certain order, you will have actually this amount which is stored in order table. So this information is available elsewhere. However, we can also have it in the order table. And should we have or not? It's actually, as I said, it's difficult to say. What is the reason of us willing to have this column? Even though we can actually calculate this information from elsewhere, and you already know that relational databases, they very much dislike duplication. So having this amount column is example of duplication because this information is already available. But by placing amount column into order table, we can save much time if we need to query order table for certain amount. For example, we need to return all orders which have a total amount of more than $1,000, and we don't care about other orders. We can do it by doing calculation of all items within item table, but assume we have millions of orders and we have multiple millions of items. So we don't want to go through all millions if you only need some orders, only orders of certain amount. And in this case, this amount column can help us. However, it's very important to note that this amount column is not really very innocent. And this is because if we introduce this column, we are now responsible for maintaining it, because at some point we can change price or change quantity of some item, which should automatically reflect on the amount column. It should automatically reflect, but it will not do this within this schema. So if you're introducing amount column or any similar denormalization column, you need actually to take burden of maintaining this column. So your software now should be responsible for doing this. And this is actually why we can work out some kind of simple rule, even though it's not very simple in real life, but let's actually assume that at least we will be following this rule. It will help us. If we decide to denormalize something, we need to know why we are doing this. So in this particular case, we are doing it in order to speed up the query for order table. So let's do it by this reason, and not because we just don't know how to do relational design properly. In your real life, you will see actually many examples of denormalization in relational databases, and there will be two reasons for this. One reason is people who designed it simply didn't follow rules and simply didn't know how to design properly. And another case is the one which we just explained it here. They might did it deliberately. They might saw some benefit of this. So let's make sure that when you design databases, it's just the second option. So you do it because you have some reason for this and not because you do not understand how to do it properly. And another important thing, which we just explained it, you need to realize that you now created additional burden. So you now have duty of updating this column. And obviously, it could be difficult sometimes, because sometimes you have many pieces of software. They may be updating your database independently. So now you need to make sure that every update to item table also updates order table. And finally, there is very interesting and very tricky question. This denormalization, is it actually good for performance? Is it bad for performance? Is it relevant? It's a very interesting question, because the entire reason why denormalization is done is normally to improve performance. However, whether it improves it or not, it's not very clear, because it will obviously improve performance of your query against order table. You will be able to query it much faster. But at the same time, it will degrade performance when you update item table, because now instead of doing one operation, updating one record, for example, updating price, you need to do two operations. You need to update your price, then you need to recalculate your amount and also update order table. So actually, you are doing at least twice more actions than you would be doing otherwise. So for update query, this denormalization is actually bringing performance down. For some select queries which are querying order table, it will be bringing it up. So you need to find some balance, what is more important for you. And now, once we did this separation of concern, we can now perform different type of queries, and we can actually approach our tables from different sides. For example, one of the typical query, which probably we will be doing frequently, is query which is retrieving customer profile. For example, we have some web page and we want to display information for customer, and we need to present his name, his contact details, his phone numbers, and also all orders he ever placed, and also we need to give breakdown what items were ordered in this order. In this case, we start our query from customer table. This is actually our driving table, because we're getting information about customer. And then we join order table with customer. You remember that our select statement can join tables. And then we also attach item table to this. So we join item table now with order table, and we query all three tables. But this is only one example of query. We can actually do very different query. For example, let's consider that we need information about items which require special packaging. Probably some items are fragile or they contain some chemicals, so they require some special packaging. And if we need to establish what packaging materials we need for this, in this case, we just go directly to item table and we query this table. And what is important to note in this case that for this query, we only need this table. We actually don't care who is customer for this order. We also don't care what order these items belong to. When they were ordered, it's not really important for this kind of query because we are only concentrated on special packaging needs. So in this case, our item table is the only table we need. And as you can see, we now start actually from the bottom. In previous query, we started from top. Our top level was customer. In this query, we start in opposite direction. We start from item. And if we slightly modify this query, probably we don't need just to know packaging materials, but we also need to query items with special packaging needs and which are not shipped yet. So for these orders which we are only going to ship but not shipped yet, for example, this is another query. This is when you're, for example, manager of some kind of warehouse which is shipping, and you need to actually only care about items which are not yet shipped. You don't care about previous items. So in this case, you join with order table. And again, you start from item table because you mostly care about item and you only need order table in order to find out whether this order has been shipped or not yet. So yet another example of query, and as you see, we're now approaching our tables in a very different direction. Now, one more type of query is a query for orders in certain status. For example, we just need list of orders which are, let's say, delayed or some kind of future orders, and we don't care about anything else. So for this query, it's not important what items are in query, and it's also not important what customer this order is for. So now you see we're approaching our tables in the middle level. So we don't start either from top or from bottom, and instead go directly to our middle level, which is order. Or for example, we need orders of customers of certain type. For example, we have business customers and we have customers who are private individuals, and we need, let's say, orders of only business customers. In this case, again, we involve two tables. In this case, the top level and the middle level. And we start from customer. So we find out what customers of certain type we have, and then we join order table with this customer and we perform this query. So you now see that actually that we're doing all varieties of queries, and for all of them, we are using the same design. Our design is following our entity rule. So one table for one entity, or one entity goes to one table, so whatever sequence you like. And our design actually doesn't depend on what kind of query we're going to execute. And this is very actually relational approach. This statement is very specific for relational databases because other databases may follow different design guidance. Within relational databases, normally when you are doing design, you are not concentrated on any particular query. We just illustrated that with this design, we can run a big variety of queries. And obviously, I presented only very small portion of queries which you can execute. You can do probably hundreds of queries against these three tables alone. And if you have more tables, you can run even more queries. However, there are also some exceptions from this rule. I mean, the rule that your design doesn't depend on query. And one of these exceptions you have already seen in previous slide, and that was, if you remember, introduction of amount column within order table. This was example when you wanted to please particular query. So particular query which is looking for orders which are which have bigger than a certain amount, they actually require introduction of this column. So there are some examples where we can step away from this rule, but as a general rule, within relational database, you design for entities and you do not design for particular queries. And no matter what queries you have, your design is equally easy because it's based on different rules, and not based on queries, but rather on some design guidance. Or if you wish, you can say equally difficult. It very much depends whether you have optimistic view on this or pessimistic view. So from optimistic point of view, you can say that your design is equally easy regardless of query, and from pessimistic point of view, you can say that your design is equally difficult regardless of what query you need to execute. Actually, these two statements are bringing the same idea. They're saying essentially the same thing, because they both actually essentially mean that you have the same amount of efforts regardless of what query you're going to execute. And another note which worth mentioning is that other database models, in particular document-oriented database model, actually do not have this approach. They do not have approach that design doesn't depend on query, and they do rely on what queries you're going to execute. So they are more tuned for specific queries. They have database structure which is making execution of some query very easy and making them very performant, while some other queries may be difficult to execute against this structure. We are not going into details here, but just interesting to mention this difference. Within relational database, you don't that much care about queries. With the other database models, you are more interested actually what queries you're going to execute, and based on this, you may be picking up your design solutions. Now let's see once again how it all works in practice. So first of all, we need to create tables we will be working with. Here you see two scripts for customer table and for customer order table. And as I already mentioned, they are not currently perfectly designed because we still have some fields like customer type or order type, which are simply text fields, and ideally they should be referencing their separate tables. But I don't have time to do everything perfectly, and I also don't want to make things too complicated. So I decided just to put comments on this. So you see there are comments saying that this should be actually customer type ID, and this, for example, status should be status ID. So these are tables which we need to create, and another interesting note is actually shown in this comment. I wanted ideally to call this table order because this is what it actually is. However, unfortunately, order is a keyword in SQL, so you cannot use it as a table name. Actually, you can use, but in this case, you will have many troubles. And also we need item table. The script for this table is currently shown. And once again, there are actually some kind of improvement which could be made in future. For example, instead of product, it would be better to have reference to product. But at this time, in the meantime, we will keep it simple as a text string. So I already went ahead and executed scripts for creating of our tables. You can now see that our tables customer, customer order, and item has been created. And the next step will be to insert data into these tables. And now we use statement which you already know, insert with values clause. However, there is one interesting thing here. You can see actually you have two new statements, set identity insert on and off. What it means, as you see, I put ID column into the list of columns where I want to insert data. However, this is actually automatic column. SQL Server assigns this column automatically. So I could actually omit this column and this insert statement will work perfectly. However, for the purpose of this example, I need more control. I need to make sure that ID for the customer is known to me. So I explicitly put three values, 1, 2, and 3. I don't want that SQL Server does this job for me. I don't want that SQL Server assigns number to these customers because I want to make sure that they're actually 1, 2, 3 and not anything else. And in order to do this, you can do this. So you can insert particular value even into column which is otherwise automatically populated. But in order to allow SQL Server to do this, you need to use this statement, set identity insert on, which means that you are allowing SQL Server to accept particular value which will be passing, and at the end you need actually to close it off. So you need to execute opposite statement, set identity and insert customer off. And now I'm using similar trick with customer order table. The similar trick, I mean that again, I put explicit value into ID column. So I don't want automatic values to be assigned. So again, I execute another identity insert statement on and then off at the end when I finished. And now I insert particular value 1, 2, 3, 4, 5, the value I wanted. And actually, the purpose of this trick becomes known if you look at second column, which is customer ID. So this is why I wanted customer ID to be known value, because in my next insert statement, I want to use them. So I put customer ID here, and now I, with confidence, can say 1, 2, 2, 2, 2, 2, 3, which means that I'm sure that I'm having customers with this ID, because these were IDs I explicitly assigned to them. And finally, we inserting data into our item table. But as you can see, now something is different. There is no set identity insert statement here. And this is because I do not need this trick. For item IDs, I can just take whatever ID SQL Server will be assigning, because I do not make any reference to this. There is another ID, order ID. And for this, I already assign a particular value, which are currently shown in the first column. And now I can refer to them with confidence. So at this point, we have all our tables ready. We have customer, customer order, and item tables created. And we have already filled them with data. So now let's go ahead and try to write queries we were talking about earlier. We were talking about the fact that we can run very different queries against these three tables and approach them from different sides. The first query is probably the most basic one, and this is query which will return customer profile. So we want data about particular customer and all his orders, and each order should show all items which are included in this order. Let's start from simple select statement. We're already familiar with select statement. At this time, it has only one table customer. And I included 3 columns, name, address, customer type. We have more columns in the table, but we can only select columns we need. And we didn't select ID column because this is not what end user wants to see. However, this ID column will be used anyway because SQL Server will use it for join. It will be joining in this column with customer order table. Let's add this join. So I'm typing in join customer order. And now I need to specify on which column we will be joining. So we will take customer table and its ID column. And we will be joining it with customer order table. And in customer order, we will take customer ID column. So we now joined already with customer order, and we want to include some items from our item table as well. In order to do this, we need to do another join. And as you can see, a single select statement can have multiple joins. You can join many tables together within one statement. So this time we're joining with item table. And item table will be joining with customer order table. It would not directly join to customer table. However, it will logically join customer table via customer order table. So join item on, and we will be joining item order ID with customer order table and its ID, its primary key. So now we have all tables together, and as we have, then we can add more columns into our select statement. We started only with columns coming from customer table, but now we can include columns from customer order table. I don't need customer ID. This is not what our users want to see, but I want order day, certainly. I want order status. And order type would be good as well. And let's include now items, columns from item table. We don't need all these IDs, but we will certainly want to know product. price quantity. And let's finish on this. So let's not include special packaging. Let's say that for the purpose of this query, we don't need it. Now we need to put our where clause because we are looking at particular customer. In this form, this statement will also work without where clause, but in this case, it will return all customers. And I wanted particular customer. I wanted customer with ID 2. So I'm typing customer ID equal to. We are almost there, but still something is missing. What is missing is order by part, because in this form it may return something in inconvenient order. I really want that all items for all orders are placed together. And I also don't want items in random order even within an order, because I want this order to be consistent. I want that when next time I run the statement, they come the same. So in this case, I'm ordering by two fields. One of them will be customer order ID. It will make sure that that items for all orders are grouped together, and items themselves, I also want them to be ordered by item ID. I just decided that it probably would be better to order by order date instead of ID. I think it will be better because this is more relevant, this is more important. However, as you can see, and this is also important, I still will be ordering by customer order ID as well. And this is because it's quite possible that two orders will have the same date. So I still need to ensure that if I have orders within the same date, that they are always presented consistently in the same order as it was before. So we are now done. What is left is to execute the statement, what I'm currently doing. And you can currently see this big table. I need to scroll it a little bit to the right and to the left in order for you to see entire table, and you can see what has been returned. So we have actually name and address are the same for all records because it's one customer, it's type business. Now, as you see, we have different order dates. We have March 2nd, March 3rd, March 5th. And for each order, we have status order type, and within each order, we have list of items. For example, these three rows are apparently coming from the same order. So within this order, there are 3 items ordered. Now we can run another query, which is a query returning all items which require special packaging. And this case illustrates the fact that we can approach our hierarchical system from different levels. At this time, we will be only looking at bottom level, at item table. We don't need to know customer or order for this purpose if we just want to have list of items. The only table we need is item table, and I already wrote this query. It's a very simple select query. And the where clause says special packaging equal 1 means it does require special packaging. So if I run this query, I will now execute it. As you can see, I have very simple list. There are only 2 items in our system, porcelain dishes and wall clock. They are both fragile and they both require special packaging. So if I just want to have list of items, I'm only looking at item table and I don't care about other table. This is example of separation of concerns. Every table stores only one entity, so we don't need to query anything else. However, let's little bit complicate this query. Let's say that we still require item with special packaging, but we only want it for orders which are not shipped yet, so orders which are in pending state. So we essentially want to know what we need to package. Those which were packaged before are already beyond of our interest. And if you remember, this information about order status is within our customer order table. It's not within item table. So what we need to do, you probably already understand, we need to join with this table. So this time we are adding one more table into this query. From item and then join customer order. Customer order, right spelling. So customer order is joining order table by order ID column. Excuse me. Join customer order. I forgot to say on. Join customer order on customer order. From customer order, we are taking ID equal item order ID. So we have joined these two tables, and at this time we already have right to put some column from our customer order table, because now it's also present in query. So I put comma here, and we want to put status. And now we run this query again. And this time we see actually the status of both of these items is pending. It means they're both not yet shipped yet, and this is exactly what we wanted. However, we may not want to review it manually, so we want actually to order SQL Server to return us all the items which are in pending status. We don't want to see anything else. So in this case, we make some modification to where clause. So we make another restriction. Our first restriction is special packaging. So we will only return these items. And we want one more restriction. We want restriction that status is pending. So in this case, we type and, adding another restriction, and now we can use columns on another table because we joined it, and we say status equal pending. We would now have the same results as they were both pending anyway, but this time no other items other than statuses, other than items with from orders which are in pending status would appear in our query results. Our next query, we will return orders which are in certain status. And it is another illustration of separation of concerns, because in order to deal with orders and their statuses, we only need one table, which is customer order. We don't care about what items are in this order or what customer this order belongs to. So we will write another select statement. I have chosen order date, status, and order type as returned column. It's returned from customer order table. And if we want particular status, for example, we want only new orders, only orders which were placed recently and not yet reviewed and not yet approved. So at first, our all orders have status new, and after that, they go to different stage, pending, shipped, completed, or whatever stage it is. So if we only want to know, for example, we are person who is approving these orders, we only want orders which are not yet approved. So in this case, we issue a query where status equal new. Status equal new. And as always, I would say as a courtesy, whoever looking at this list, we need order by. We don't want anybody to see unordered list where items are presented in some inaccurate manner, so we will order them. Probably it will make sense to order them by order type, and within the same order type, probably order date would be another good choice. So they ordered first by type, and then within the same type, they ordered by order date. So now we execute this statement and see that we only have two orders which are new. And this time we want orders of customers of certain type. For example, we only want orders from business customers. Let's say that we need to pay some kind of special tax, which is only charged when customer is business and not a private person. So in this case, as we need orders, we obviously need to query customer order table. And I already put this statement, and again, I'm retrieving order date, status, and order type. However, information about customer type is within customer table because it describes customer, it doesn't describe order. So how do we do it if information is in different table? I think you already know the answer. We need to join with this table. So let's go ahead and add this join. So from customer order, join customer table on customer order, customer ID equal to customer ID. So as soon as we have another table in our list of tables, we can now issue where clause for any column of any table we have in our join. So we can restrict it by orders or by customers. This time we're restricting it by customers. So we need to put what is called customer type, where customer type equal business. And don't forget to put at least one order by here, because we always want our results to be presented in some kind of nice and readable form. Let's order it by order date this time. So it's all done. Let's execute this statement. And now we see orders which are only came from business customers. All done. This is end of part 3 of this video series. And now you are invited to watch part 4, which will be talking about another interesting topic. At the very beginning of this series, I might somehow intrigue you when I say that any kind of data, even data of very non-tabular form, could be actually finally fit into tables. And this part 4 actually will be talking about this subject. How do we fit any kind of data into tables? So see you later in part 4.